Hi guys, so welcome to another video. In this video I'm going to talk about arithmetic sequences and series and understanding the summation formula. Now you might already know, and you probably already know, that the summation formula for an arithmetic series can be expressed as S of n is equal to n over 2 multiplied by u1 plus un. Now we can obviously prove this by induction, but that's not very interesting. So instead, what I wanted to show is how to derive this and why this is true. Because I feel like that gives a much better insight as to why it works than just showing that it is true. And this is actually related to an interesting anecdote to a famous mathematician called Gauss, who was a child genius and a prodigy. And apparently, when he was asked this question, he gave an answer in only a few seconds. So let's consider some kind of arithmetic sequence, just a sequence of natural numbers, and we're going to add them up together, so we're going to get an arithmetic series. Just say 1 plus 2 plus 3 plus 4 plus 5, 6, and so on until 100. And apparently, according to the legend, Gauss was able to figure out how to calculate this instantly without even knowing the formula for arithmetic sums. Actually, I should probably write that a bit bigger. Okay, so we have our arithmetic series here. Now I already know the formula, but how can we actually figure this out? Actually, something that you might notice if you pay attention to the series is that we can order it in a pretty interesting way. Actually, it's going to help if I write out some terms. What you might notice is that as we move across the series and we add together corresponding terms from the beginning of the series and the end of the series, we're actually going to end up getting the same sum. So, for example, let's take 1, 100. 1 plus 100 gives 101. 2, 99 gives us the same sum. 3, and 98. Same thing. 4, 97. 5, 96. Okay, and if you don't believe me, you can try all the terms, then you'll see that the sum is always the same. So what do we see? When we take these pairs of integers from the end of the series and the beginning of the series, we actually always get the same sum. Now, if we have 100 digits, or 100 numbers rather, that must mean that we're going to have 50 pairs. So the sum of this, the sum of these 100, can be expressed as half of all the digits, right? Because we're essentially bundling them up as pairs. So however many digits you have, you add together pairs which give you the same sum. So in this case, it's going to be 100 over 2, because there's 100 total digits. But since we're pairing them together, there's going to be 50 pairs. And each pair gives us the same sum. In this case, it's 1 plus 101, which gives us 50. Oh, that should be 1 plus 100. That's 50 times 101. And I'm not sure what that is, but that doesn't matter. That essentially shows us how to derive this. And this obviously works with any n number of terms. Right, so let's just try this for any n number of terms rather than just 100, just to show that this can also be generalized. And then you can also prove this by induction, but that's a quite simple proof, so I'm not going to show it here. 1 plus 2 plus 3 plus 4 plus n, n minus 4 plus n minus 3, n minus 2 plus, or never mind, it should be n minus 3. And actually, just by considering this, you're also going to find something interesting which can be related to the triangular numbers, which I'll show right after I cover this. So let's just apply the same concept. 1 plus n, that gives us n plus 1. 2 plus n minus 1. Once again, 2 minus 1 gives us 1, so that's also n plus 1. 3 plus n minus 2 is equal to n plus 1, and so on. And since we have n numbers, that must mean that we're going to have n over 2 pairs. So the sum of this is going to be n over 2 multiplied by 1 plus n. Right? And when it's expressed as a arithmetic series, it's better to write it in terms of the terms, in terms of the positions of the terms in the series. So that can be written as n over 2 multiplied by u1 plus un. So that shows how to derive the formula for an arithmetic series, and hopefully that makes sense. And just as an additional caveat, in addition to that, what I've just shown here, using actually the same idea of an arithmetic series, is how to find the sum of the first n natural numbers. And if you remember, what I just wrote was n multiplied by n multiplied by n plus 1 over 2. Now, why is this interesting? The reason why this is interesting is because although this is the sum of the natural numbers, this is also a way of finding certain numbers called triangular numbers. And the reason why they're called triangular numbers is best explained visually. So, okay, let's see. Let's take 1. 1 plus nothing is just itself. 1 plus 2 equals 3. 1 plus 2 plus 3 equals 6. 1 plus 2 plus 3 plus 4 equals 10. 1 plus 2 plus 3 plus 4 plus 5 equals 15. 1 plus 2 plus 3 plus 4 plus 5 plus 6 equals 21, and so on. But actually, what you might find interesting here is that this can be expressed using the same formula. Now let's see this. So we have the sequence 1, 3, 6, 10, 15, 21, and so on. So we have u1 equals 1, u2 equals 3, u3 equals 6, u4 equals 10, u5 equals 15, and u6 equals 21. Now let's try to plug in these n's and see what we get. So 1 multiplied by 1 plus 1 divided by 2 is equal to 1 times 2 divided by 2. The 2's cancel, and we get 1. Let's try it for 2. 2 multiplied by 1 plus 2 divided by 2. Again, the 2's cancel, we get 1 plus 2, that's 3. Let's try it for 3. 3 multiplied by 1 plus 3 divided by 2. 2's don't cancel, actually they do in the 4. So we get 3 multiplied by 1 plus 3, that's 4. 12 divided by 2, that's 6. 4 multiplied by 1 plus 4 2 is equal to 4 times 5 divided by 2, which is 10, and so on. Now, why are these called triangular numbers? Actually, for the same reason that square numbers are called square numbers, because if you try to write out equilateral triangles, you're always going to get these numbers, and you'll see why in a second. So let's say that we're trying to make triangles which consist of rows which are one larger than the one before it. So what does that mean? First, we just have a single ball. We're going to try to make triangles out of these balls. So first we have 1, then it was the next triangular number 2 times 2 plus 1, so now we have 3. The most basic triangle that we can get. So these 3 dots on top of each other. Then we add another row, but obviously we have to add 3 dots in this case. Here we have 6. And this should make sense because if you just consider what we're doing, we're basically just adding together the same natural numbers that we just found. So here was 1, here it's 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and so on. And these numbers actually have lots of really interesting properties if you study them further. And maybe I'll cover that in another video. Now, we have also shown that the sum of an arithmetic series can be expressed as n over 2 multiplied by u1 plus un. But if we think back as to what an arithmetic series means, an arithmetic series is defined by the fact that every single term has a constant difference, right? So if I want to write u2, I can write that in terms of u1 as u1 plus d. If I want to write u3, then my first term plus 2d, and so on. So if I want to write un, that's u1 plus n minus 1 times d. Which is why sometimes you're also going to see this written in a different way. And in the IB formula booklet, I'm pretty sure it's written in both ways. So you can choose which one to use based on which information you have. Yeah. And that's the other form that you're going to see in your final booklet.